Welcome to Study Loop.
All right, we've got the question here that describes a ladder that is being inclined onto a wall. Okay, this line here is the ladder. This here is the wall. And we have an angle, theta, that shows a relationship between the two. And if we're told that the bottom of the ladder is 6 feet from the wall, okay, and we also know that the ladder is given to us if we look at example 2. The ladder is 10 feet long. Then we want to determine how fast the angle here is, theta, is changing as the ladder is pulled back. Okay, so as the ladder is pulled back from the bottom, how fast is that angle changing? Excuse me. All right, so first what we can do is we can use the Pythagorean theorem to get this side here of the wall. So we have x squared plus y squared equals c squared. And here we know our z squared is the hypotenuse. So 10 squared is equal to 100. And then our x squared is 6 here. So 6 squared is 36. So now we solve for y squared equals to 100 minus 36. And y will be square root of 64 because we know 100 minus 36 is 64. So we're left with 8 feet. Okay, so our 8 feet will be our y. All right, now we can use a sine function to describe theta. And we'll say, well, sine of theta is equal to the opposite, which is y here, over hypotenuse, which is 10. Now we know what our y is. We just calculated for it. So we'll say that's 8 over 10. And so if we take the sine, excuse me, if we differentiate now, we can calculate for the change in theta. So we would do actually, it'll probably be easier if we write out the cosine function as well, because we know whenever we derive a sine, we end up getting a cosine. So let's also calculate for cosine theta. So cosine theta would be adjacent over hypotenuse, which is 6 over 10. Okay, now let's go ahead and differentiate that cosine so we can get a negative sine theta d theta over dt. Once again, just to clarify, we are taking the derivative of that so that we can get the change of theta over the change in time. And we would have all of that equal to a, well, here, so the variable that is changing, right, is this distance here. Right? I've just realized that. So since that distance is changing, we can also keep it as a variable x, so that when we do take the derivative, we will get x over 10. And then you take the derivative of x, that'll go to 1. And then you have dx over dt. stylus is acting up. Okay, there it goes. So we have d x over well, this is for some reason my stylus is acting up, so I'm going to go ahead and move it over to this side. For some reason it doesn't like that spot there, so we're saying that this is equal to this here, which would be 1 over 10 dx over dt. Okay. Now, if we go ahead and move everything over and only leave d theta over dt on one side, then we'd have a 1 over e negative sine theta multiplied by 10. Okay, and then that would be multiplied by dx dt. So, sorry, for some reason it's not liking that this middle area here, so it won't let me draw there. So I'm going to move it over. So we have negative 1 over sine, 10 sine theta. And we have dx dt. All right, now we're told that the change of x, as it's moving across the ground, it occurs at 1 feet per second. And we know sine theta we've already calculated for over here, right? We've already calculated that as 8 over 10. So we can plug in all the values now. So we have d theta over dt is equal to negative 10 times 8 over 10. These will cancel out, multiplied by 1, because we're told that it's moving at 1 feet per second. So our change in theta, finally, over time will be equal to negative 1 over 8 radians per second. All right, and that'll be our final answer there. All right, well, I hope that clarifies the question. Thank you so much for watching.